Good morning, students. In our last class, we discussed about p-type and n-type semiconductors. Now we discussed about Hall effect. The Hall effect was discovered by E.H. Hall in 1879. Hall effect was discovered by E.H. Hall in 1879. Now we know about what is Hall effect. The perpendicular magnetic field is applied on current carrying conductor. The potential is developed between the 2 points on opposite ends of the conductor. This is called Hall effect. The perpendicular magnetic field is applied on current carrying conductor. The potential is developed between the 2 points on opposite ends of the conductor. This is called Hall effect. For that purpose, consider current consider a conductor Now the conductor is connected with batteries, positive, negative, positive, negative, positive. This is current carrying conductor. Now magnetic field is applied perpendicular to the current carrying conductor. Potential is developed potential is developed at between the 2 points on opposite ends of the conductor. VH. The developed potential is called Hall voltage. This is VH, current carrying conductor. Charge acquires on the opposite ends of the conductors. Charge acquires on the opposite ends of the conductor. This is called Hall effect. The perpendicular magnetic field is applied on current carrying conductor. The potential is developed between the 2 points on opposite ends of the conductor. This is called Hall effect. Current carrying conductor, applied the magnetic field is applied perpendicular. Potential is developed between the 2 points on the opposite ends of the conductor. Potential is developed between the 2 points on the opposite sides of the conductor. This is called as Hall effect. Now, the current in the conductor along x-axis, the magnetic field is along y-axis. Then the force is developed due to magnetic field along z-axis. Current passing through the conductor is represents along the x-axis. Magnetic field is applied on the conductor represents y-axis. Then the magnetic force is developed due to the applied magnetic field along the z-axis. The direction of force represents by Fleming left hand rule. The current in the conductor represents along x-axis. Applied magnetic field represents along y-axis, and the force due to the magnetic field is along the z-axis. This is by using Fleming left hand rule. Now, magnetic deflecting force is equal to BQ VD. The magnetic deflecting force is equal to BQ VD. Here B magnetic conduction field strength, Q charge, VD is the drift velocity. Hall electric force is equal to EH into Q. This is equation 1 and this is equation 2. At equilibrium, one is equal to 2. EHQ is equal to BQ into VD. QQ cancel. EH is equal to BVD. But this is represents, this is named as equation 3. But VD is equal to J by NQ. This is named as equation 4. Here VD is drift velocity, J current density, and number of charge carriers, Q charge. Equation 4 is substituted in equation 3. Then we can getting Hall electric field EH is equal to V into J by NQ. This is named as equation 5. Hall electric field. By this equation, we can calculate the Hall voltage. Hall voltage VH. The relation between VH and EH. EH is equal to VH by D. Distance of separation between 2 points D. EH is equal to VH by D. This is named as equation 6. Now we can discuss about, once again, magnetic deflecting force is equal to BQVD. Hall electric force is equal to EHQ. At equilibrium, 1 is equal to 2. EHQ is equal to BQ into VD. EH is equal to BVD. VD is equal to J by NQ. Here VD is drift velocity, J current density, N number of charge carriers, Q with the charge. So finally, equation 4 is substituted in equation 3. EH is equal to BJ by NQ. We know the value of the EH, then we can calculate the value of Hall voltage VH. The relation between EH and VH, EH is equal to VH by D. D is the distance of separation between two points. Right. Now we can discuss about Hall coefficient. Hall coefficient or H. It is denoted by RH. The ratio of Hall electric field to product of current density and magnetic induction field strength is called Hall coefficient. So according to the definition, RH is equal to the ratio of Hall electric field to product of current density and magnetic induction field strength. RH is equal to EH by JB. This is named as equation 7. Equation 5 is substituted in equation 7. RH is equal to Bj by Nq by Jb. Finally, we can getting RH is equal to JBAB. Cancel 1 by Nq. This is the value of Hall coefficient. This is the value of Hall coefficient. If significance if the coefficient is negative, the charge carriers are carriers of electrons. Otherwise, it is positive. It is positive. The charge carriers are holes. This is the Hall coefficient. Now, applications of Hall effect. First one, Hall effect gives the information about sign of charge carriers. And second one, it can be used to measure the drift velocity. Third one, strong magnetic fields can be determined. Fourth one, it can be used to find the mobility of charge carriers. And the final one, it can be used to measure the number of charge carriers per unit volume. These are the applications of Hall effect. First one, Hall effect. Hall effect gives the information about sign of charge carriers. And the second one, it can be used to measure the drift velocity Vd. Strong magnetic fields can be determined by using Hall effect. It can be used to find the mobility of charge carriers. Mobility is the drift velocity per unit electric field. It can be used to measure the number of charge carriers per unit volume. Number of charge carriers per unit volume. Okay. This is the information about Hall effect. Hall effect explanation. Hall coefficient calculation and applications of Hall effect. Thank you all.